All right, so what we're going to look at now is we're going to look at Cartesian products. In our book, it's actually 2.6 is for in terms of what we're doing. And what an ordered pair is, we're going to start out with this definition for an ordered pair. You've probably heard of an ordered pair before because you've done math, right? Okay, and in math, an ordered pair is like x, y, okay? And the first entry is x, the second entry is y, right? And we actually oftentimes will say, well, x is just going to be pulled from some set, and y is going to be pulled from some set. All right, so we'll say, okay, well, x belongs to, we'll say, the set x, and y belongs to the set y. In algebra, xy had x coming from the reals and y coming from the reals. So x belonged to the reals, okay, and y belongs to the reals, right? That's a Cartesian coordinate. If you remember, that's your Cartesian coordinate system. Basically, it's how you graph things in algebra. From the standpoint of discrete structures, we don't actually have to have x and y coming from R in an ordered pair. And in addition to that, we don't necessarily have to have them be pairs. We can have something called an Ntuple. Okay? And an Ntuple is, what we should say, it's like a set, not a set, but rather an object made up of elements from a set. Or a set of sets. And how we might write that is we might write it like, okay, I've got x1, x2, all the way up through xn. So we've got n elements inside of the Ntuple. And so sometimes what we'll see is we'll see that, oh, well, we might get like, it might have 30 elements inside of it. It might have 100 elements. It might have a billion. I mean, like when you're talking about stuff in computer science, sometimes these Ntuples, they're massive. And then we get called vectors, and they have other qualities that we use when we talk about vectors. But basically what they are is they're a string of numbers, right? Delineated by coordinates, by commas, to say that they're coming from possibly different sets, all right? And so that's kind of that idea. It's like, oh, okay, I'm going to pull, right, an element from each one of these sets, all right? So, for example, I might have the set A, and we'll have the set A equal to red, blue, and green. We'll have the set B equal to milk, lemonade, and soda. And so we can imagine we've got call it an ordered pair here in this case, where we'll pull something from A first. We'll say red, comma, milk. Pull something from A and then pull something from B. And that's the ordering that we select to use. Okay? There it is, red, milk. We could also construct, let's call it a 4-tuple. A 4-tuple is going to be red, 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 milk. And in this case, the 4-tuple is going to have an element from A, an element from A again, an element from A again, and then milk. Okay? Now, what we want to see is that this ordered pair is coming from a set in and of itself. All right? And that set is called a Cartesian product. All right? So a Cartesian product is the set of all Ntuples from a given group of sets. And it's kind of hard to, define it this way. It's not the greatest definition. What I want to do instead is I actually want to just kind of demonstrate. You can look up what the definition of a Cartesian product is, all right? Give you something better. But basically, like say, for example, we'll look at A cross B, okay? So A cross B, this is your Cartesian product symbol. And so A cross B is going to be the set of all ordered pairs AB such that A belongs to A and B belongs to B. So basically what we're saying is, okay, well, what I'm going to do is I'm going to select a value from A, and I'm going to select a value from B, and I'm going to actually create a set that's made up of all of these. Okay? So this set, if I were to rewrite it, excuse me, there's my brackets, in curly brackets, is going to be red. I'll make that RM, red milk, blue milk, green milk, then red lemonade, RL, blue lemonade, green lemonade, and then red soda, blue soda, green soda. And that's the set of all elements inside of the set, right? In A cross B. All right? What we're do is we're just going to pair up each and every element. Okay? So that's actually what we mean when we talk about a Cartesian product. All right? Now, we also want to talk about the cardinality of a Cartesian product as well. So the cardinality, if you remember, is how many elements are actually in that set, right, inside of A cross B. And we denote that as, right, like an absolute value symbol. A cross B is going to equal, all right, the cardinality of A times the cardinality of B. And there it is. You can actually see that. Notice that, like, say, for example, here, that's 9 elements inside of A cross B here, and that's equal to 3 times 3. The cardinality of A was 3. The cardinality of B was 3 as well. Okay? There it is. A cross B is the cardinality of A times the cardinality of B. Now, we don't necessarily also have to have just 2. Like an ordered pair, our Ntuples, okay, we can have as many sets as we want. So, for example, if we wanted, we could create this example of A cross A cross A cross B. Right? That's the second set of tuples that we saw before. All right? And this is the set of all x belonging to, and we'll call this A1, A2, A3, and B1, such that A1, A2, A3 belongs to A, and B1 belongs to B. And so that's the set that we have now. All right? And what we've done is we've actually kind of said, okay, well, I've now generated, I want to say, all right, the first 3 in this set are going to be values from A, and the fourth is going to be value from B. So an example of that we saw earlier was red, say blue, right? Because that's also coming from the set A, and then soda, because that's coming from the set B. And that's an example of a tuple there. In this case, a 4 tuple from the Cartesian product A cross A cross A cross B. If we switch the order of that Cartesian product, say we do A cross B cross A cross A, okay, then that's going to end up equaling the set of all x belonging to, let's say, A1, comma B1, comma A2, comma A3, okay, such that, and again, A1, A2, A3 will come from A, and B1 is going to come from B. So we're coming from the same sets, but what's changed is the order. Okay, notice that this order matters inside of that Cartesian product. Every tuple has to be in the correct order that goes along with the Cartesian product. So in this case, now we could look at this and say, oh, it's red, soda, red, blue. Because now the second element, okay, the second element is coming from B, which is your soda element. So that's how Cartesian products work. A Cartesian product is basically going to say, okay, well, we've got this set, right? And I'm going to pull an element from that set, and then I got another set, and I'll pull an element from that set, and I got another set, and I'm going to pull an element from that set, and I'm going to put them all together into these things called Ntuples, right? Or doubles or duples or ordered pairs, depending upon how many you have. Sometimes a triple. A triple is going to be, well, obviously it's 3. A quadruple would be 4. And after that, we just call them 5 tuples, 6 tuples. We don't use sextuples, septuples. We don't, who does that? Nobody does that. So, well, maybe they do. I don't know. You know what? Who knows? What I do know is that I call them like a 7 tuple. And then that way it makes it very clear there's 7 elements, right? You don't need to know any Greek. So that's how a Cartesian product works. By the way, if we wanted to see what the cardinality of A cross A cross A cross B was, we'll use the same equation. It's now going to be A times A times A times B, their cardinalities. And so this is 3 times 3 times 3 times 3, or 3 to the 4th, and that's 243. So there are actually going to be 243 elements in A cross A cross A cross B. There will also be 243 in A cross B cross A cross A. That's why I didn't write them all out, because there are an awful lot of them. Okay? Wait, nope, 81. Sorry, not 243, 81. That's 3 to the 4th. Right? That should equal 81. All right? Still, not going to write it all out, because 81 is going to take us a long time. If you want to, you can go ahead and do it. No problem. So now let's look at some special Cartesian products. All right, we'll start out with, we've got R, and that's the set of the reals. That's a set. We've got Z, this is the set of integers. That's got Q, we've got the rationals. And for our purposes, because we're doing discrete structures, this is really what we need. We could also go with, like, say, for example, all the whole numbers. And remember, we could have Z plus, we could have Z minus, whatever it is. So if I take R cross R, okay, R cross R, we'll notice that this is like the set of all x1, x2, okay, such that x1 and x2 both belong to the reals, okay? And that's the Cartesian coordinate system. It's also what we call, we have a name for this, this is also going to be called R2. What happens is that if you have all of the sets that you're pulling from happen to be all the same set, what you can do is you can shorthand it rather than writing the whole Cartesian coordinate system. You can just actually call it R2, right? Okay. And so what we have is we've got a double or an ordered pair with everything coming from the reals, right? And that's what we call R2. If we wanted to do something like this, R cross R cross R cross R, what we're going to get is this is going to equal R4. All right? And so that's going to end up being X1, X2, X3, and X4. Okay? So everything in there, and then X1 through X4 are all going to belong to the reals. And these are 4 tuples, and we call it R4. That is because we've got 4 R's. That's it. Okay? 4 tuples. Now, one thing to get here is that, and one of the things that a very common misconception is to think that R2, right, happens to be a subset of R4. This is wrong. Everything in R4, okay, it has to have 4 elements. Everything in R4 has to have 4 elements, all 4 of the elements coming from the reals. Everything in R2 only has 2 elements, so they don't have the same set definition, right? So consequently, R2 is not a subset of R4. That doesn't work, okay? It's wrong, right? It ends up happening because one of the reasons why people do this, or why this happens, is because the geometric description, say, for example, of R2 is this XY plane. And then we know, like in 3 dimensions, that we've actually got the XYZ volume, right, or the space XYZ, and we're like, well, XY, that plane is in XYZ. So shouldn't R2 be a subset of R3? Well, that's not true. That's actually a misconception. The whole thing with that is actually to understand that that XY plane is the geometric representation. It's not actually R2 itself. Okay? And R3 is not actually the XYZ plane. It's a representation of R3. All right? So we want to get that these actually are not subsets. All right? Same thing if I have, say, for example, I've got Z cross Z cross Z. All right? That's equal to what we call Z3. All right? Or Z cubed. And that's going to be, we'll call this X1, X2, X3. Right? And now instead, therefore, with such that X1, X2, and X3 are all going to belong to Z. And we can do the same thing with Q. We can do a lot of things with these elements. Okay? So what you want to get here with our special Cartesian sets is basically we have a special way of notating them. We have a special way of notating them. And that is that if they are all coming from if every element's coming from the same set, we can basically like raise it to a power. Even though that's not really what's happening, that's what it looks like, and that's one of the things that we do. Okay? Remember that if I see R2, those are going to be ordered pairs where every element is coming from the reals. If I see Z3, these are triples where everything is coming from the integers. Okay? And those are our sets of special Cartesian products. Now, when we construct Cartesian products with infinite sets, what we want to do is we want to realize that we're going to get different kind of cardinalities. All right? So let's say, for example, I take R from my previous example and I cross it with A, right? That set that actually had only 3 elements. And I want to know what is its cardinality. Well, it still holds that it's going to be R cross A. But in this case, R has an infinite number of elements times the 3 elements in A. Well, 3 times an infinity is going to be just simply infinity. There's an infinite number of elements in R cross A. I mean, basically we have what's called an uncountably infinite number of elements, but we're not going to get into the uncountability right now. We just want to know, you know what, it's got an infinite number of elements, and so what I'm going to have to do is I'm going to have to like construct a set builder notation way of representing R cross A. If we take, for example, now, like say we've got Z and we cross it with R, okay, that's going to have Z cross Z, or Z times Z, and that's just infinity times infinity, and that is still infinity, all right? Or excuse me, Z times R, and that's infinity times infinity, and that's just infinity. Now it turns out in a really weird way, from a really mathy perspective, and we won't get too much into it today, beyond the scope of this course at the moment, is that actually this infinity that we see right here, this infinity, is in fact bigger than just the infinity for Z or the infinity for R by itself. It's a little weird, right? Okay. Or, well, actually, it's bigger than the infinity for Z, and I have to think about whether or not it's bigger than the infinity for R. It might be the same size. But what happens is that mathematically, when we talk about cardinality, we start to get into some really interesting things happening whenever we work with infinite sets. Okay? But if we are going to construct a Cartesian product with an infinite set, you just got to know that its cardinality is going to end up being infinite.